have a look at the screen. You can see two pictures. The first is of ice creams kept in a freezer, while the other is also ice cream but kept outside at room temperature. So my question is, can you calculate the time required for this ice cream to melt completely? Let us find out if we can. Here is something else that we come across every day. This is a hot cup of coffee. You can see the steam rising from it, which tells you that it is very hot. So the question is, what happens if we keep it outside for some time? Definitely, it cools down. But after how long? In order to find out the answer to questions like these, let's take some help from Mr. Newton. So Mr. Isaac Newton came up with a famous law of cooling. Let's have a look at the definition. It states that the rate of heat loss from a body is directly proportional to the difference in the temperature of the body and the surroundings. If you were to actually monitor the rate at which a body was losing heat and becoming cooler and tracking the temperature as you can see here, you would notice that this rate of change of temperature is not uniform. Initially, the slope is pretty steep, which tells you that the object is losing temperature pretty fast. But as the object cools down, you notice that the rate of cooling is also slowing down. Let's try to understand why this is happening. We can infer initially that the rate of cooling is higher and it is decreasing as the temperature of the body falls. We can use some help from mathematics to understand why this happens. Let's take a look at the amount of heat energy carried by this object. Take Q as the amount of heat in the body and delta Q is the change in the amount of heat in the body, and let T be the time taken for the loss of this heat energy. So the loss of heat can be modeled as negative dQ by dt or the negative derivative of heat with respect to time. The negative sign indicates that the change is negative. That is, the final heat energy of the object is less than the initial heat energy of the object. There is something extra added in this equation, that is the negative sign. What does it for? It indicates that heat is being lost from the body, so the slope of the graph will be negative. That is, the initial heat energy was greater than the final heat energy of the object. The question is the loss of heat energy and the change in temperature linear with respect to each other? Let's find out. Let's take the temperature of the surroundings and the body as T1 and T2. So we can write minus dQ by dt is equal to small k times T2 minus T1. Here k is a constant depending on the area and the nature of the surface of this body, as all bodies don't have the same surface or the same color. Now, suppose the mass of the object or body is m and its specific heat capacity is small s. If the temperature of the object is falling by a small amount, let's say it is dT2 in time dt, then the amount of heat loss can be written as dQ is equal to m times s times dT2. So this is the equation that we get based on this assumption. In the beginning of the derivation, we wrote the equation for the rate of heat loss. Now we can substitute the value of dQ in the left hand side of this equation. Now the rate of heat loss is obtained as minus dQ by dt, which is equal to minus m times s times dt2 by dt. Now, both of these equations are equal since their right hand sides are equal. On equating these equations, we get minus m times s times dt2 by dt is equal to k times bracket t2 minus t1. Rearrange the equations by putting the terms containing t on the left side and the others on the right side of the equal sign. Instead of small k, we will use m times s specified as capital K. If we integrate this equation, we get the result log t2 minus t1 is equal to negative capital K times small t plus c. Here, small c is the constant of integration. To eliminate the logarithm, we can take the exponential of both sides and this gives us a new constant capital C. We get the equation t2 is equal to t1 plus c dash times e raised to the power negative capital K times t. So what are the applications of Newton's law of cooling? Well, for one thing, we can estimate how much time it will take for an object with a given set of properties to go from one temperature to a lower temperature. We can find out how much time it will take for a soda placed in a fridge to cool down to the same temperature as the fridge. You can calculate how much time it takes for the ice cream to melt, and many other applications limited only by our imagination. So let's summarize what we have learned so far.
Manorama Horizon. Learning made simple.